Next thing we want to talk about is in more detail look at how we can analyze sequences. So we've kind of introduced sequences, introduced series, how they're different. We've talked in general about some of the things we want to do with them. So we're going to get in more detail with sequences now and look at how we can analyze them. Okay. So we can we can look at them as so what you could do is look at how um, an analogous function. So we've already talked about how some of these sequences have limits and some of them diverge. Okay, the ones that have a unique limit we say converge. But how do we assess that? Well, we could do that by looking at the sequence in the same way we would look at an analogous function. And so consider, for example, the sequence a sub n equals n over n plus 1. Okay. Now that sequence occurs for integer values of n. So these are discrete values that we can see here. First, we've got a1 would be 1/2, and then we've got um, 2/3, and so on, right? So these red dots are the discrete values of the sequence. But if we want to know what the sequence converges to, I can look at the analogous function where I swap the n's for x's. And so I get this function f of x equals x over x plus 1. And if I look at the limit of that function as x goes to infinity, if that limit exists, it will be the same as the limit of that sequence. Okay, so let me just do that real quick in detail, right? So here's our, okay, that's what we're interested in. Okay, so I want to look at the limit as n goes to infinity of a sub n. So that's the limit as n goes to infinity of n over n plus 1. Okay. If I look at the analogous function and I take the limit as x goes to infinity of that function, okay, and if you remember how we can do that, what we're really looking at is how, relatively how fast the numerator and denominator approach zero. So I can divide by x, divide everything by x. So I'm going to get 1 over 1 plus 1 over x. That part's going to go to 0. This whole thing's going to go to 1. And so this sequence would also have to go to 1. Okay, and I'll scoot that down so we can get a better view there. Okay, so that is the process that we're looking at here. Okay, so limits of sequences from limits of functions. Suppose f is a function such that f of n equals a sub n, right? F of n equals the nth term in the sequence for positive integers n. If the limit as x goes to infinity of f of x equals L, then the limit of the sequence a sub n is also L. And that limit could also be infinite, could be plus or minus infinity. Okay. Now, with that in mind, we have limit laws for sequences, and they are same, analogous to those for functions. If we have a sequences a sub n and b sub n, and they have limits a and b respectively, then the limit of the sum or difference of the sequences is the sum or difference of the limits. The limit of a constant times the sequence is the constant times the limit of the product of the sequences, the product of the limits, and the limit of the quotient of the sequences is the quotient of the limits, provided that b, the denominator, is not 0. Okay, some definitions, some terminology that's going to be important. We're going to talk about whether sequences are increasing or decreasing, first of all. So let's talk about increasing or non-decreasing sequences. So increasing means the terms get successively bigger. So the n plus first term is bigger than the nth term. Okay. The natural numbers are one such sequence: 0, 1, 2, 3. Okay. Non-decreasing means the n plus first term is at least as big as the nth term. So it's equal to or larger than the term before it. Okay, 1, 1, 2, 2, 3, 3 is an example of a non-decreasing sequence. It's not increasing because the terms don't keep getting larger all the time, but they do not get smaller. Okay, decreasing means they do get smaller. The n plus first term is less than the nth term. Okay, 2, 1, 0, minus 1, minus 2, and so on. Non-increasing means that the terms are not getting larger. Okay, they're staying the same or getting smaller. Okay, so it goes without saying that increasing sequences are also non-decreasing sequences. Decreasing sequences are also non-increasing sequences. And finally, a very important term, if you have a sequence that is either non-increasing or non-decreasing, okay, so increasing or non-decreasing, decreasing or non-decreasing, it's monotonic, okay? Monotonic means it's moving in just one direction, okay? So a decreasing or increasing sequence would be monotonic, but one that gets smaller and then gets larger, that is not, okay? Getting smaller or staying the same, that's monotonic. Getting larger or staying the same, that's monotonic. But when a sequence changes directions, okay, so we get smaller, then larger, then smaller, then larger, for example, that's not a monotonic sequence. Finally, we have boundedness. If a sequence is bounded above, if there is a number m such that all the terms in the sequence are less than or equal to that number. Okay. A sub n is bounded below if there is a number n such that all the terms in the sequence are greater than or equal to that number. Okay. And if a sub n is bounded both above and below, we say that a sub n is a bounded sequence. And that the boundedness is for all relevant values of n. So going back here, for example, if we define this sequence for n equals 0, 1, 2, and so on, then all we care about are for the values of n for which the sequence is defined. Okay. So I don't care about, so I would say that this sequence is bounded because for all the relevant terms, it's bounded below by 0, it's bounded above by 1, so it's bounded. I don't say, well, what happens if I plug in n equals negative 100? Okay, that's outside 0. Well, that's not one of the relative indices, relative values of n, so I don't need to consider that. Okay. Okay, so now let's talk about examples of a bounded sequence or bounded sequences. We'll look at two sequences. One, the sequence a sub n is going to be 1 plus 1 over n for n going from 1 to infinity. The other is 1 minus 1 over n for n going to 1 from 1 to infinity. In the red, that's our first sequence, our a sub n, right? And you can see the terms of this decrease. Okay, let's look at that formally, right, all we have to do is take the limit as n goes to infinity. You don't necessarily, so we have that theorem that says if there's an analogous function, et cetera, but you don't always, I don't anyway. So whatever um, your particular instructor wants you to do, you want to do it that way. But I don't write, so I wouldn't write 1 plus 1 over x and look at that function. I would just look at the limit as n goes to infinity. And so we can jump over here and do that. It's pretty straightforward here. So we have a sub n is 1 plus 1 over n. Okay. Okay, we have b sub n 1 minus 1 over n. Okay, so looking at the limit as n goes to infinity, 1 plus 1 over n. Okay. Well, carry 1 off to infinity. This term goes to 0. Of course, this goes to 1. Okay. There's 1 minus 1 over n. And we get the same thing, goes to 0, so this goes to 1. So the limit of both of these is 1. The next question is the monotonic question. All right, so we want to compare, and let's start with the a sub n term first, right? We want to compare a sub n plus 1 to a sub n. Okay, is this greater than or equal, less than or equal? Which isn't? Okay, so if we look at the n plus first term, that's going to be 1 plus 1 over n plus 1. I'm going to compare that to 1 plus 1 over n. Okay, so if I subtract 1, I'm comparing 1 plus 1 over n to 1 over n. And of course, as this number gets larger, since I'm dividing, this is always going to be smaller. Okay. The n plus first term is always going to be smaller than the nth term. Right? So I'm going to add 1 plus an increasingly smaller number. Okay, so that's always going to be smaller. And so that means that the a sub n is a decreasing, okay, sequence, which means since it's decreasing, it's monotonic. Okay, we'll look at the next one. That would be b sub n. So that's where we're going to change this to a minus sign. Okay, and we get the same limit, but now I want to do that same thing. I want to compare the n plus first term, so 1 over 1 minus n plus 1, and compare that to 1 minus 1 over n. Okay, so now, I can cancel the 1 if I wanted to, so I'm looking at negative 1 over n plus 1 compared to negative 1 over n. Well, the absolute value of 1 over n plus 1 is going to be smaller, but it's in the negative direction. So that means this is going to be greater than. So this is an increasing sequence. Increasing sequence are also monotonic. Okay. So that's how we can look at and determine whether a sequence is increasing, decreasing, or what's going on with it. So, all right, back to our graphic example. And so we can see the first one, a sub n that we looked at, that is decreasing. Okay. It's bounded because for n equals 1 to infinity, we range from 2 to 1. Okay. It's monotonic because it's decreasing and it's bounded. It's monotonic because it's going in the same direction. The other one, b sub n, ranges from 0 to 1, so it's bounded, okay? And it's increasing, so it's also monotonic, and so those you're going to the same limit, 1. Okay, so that's how we look at that. All right, so now let's look at another example here. All right, for the next sequence, we have a sub n equals n to the 3 halves divided by n to the 3 halves plus 1. So if we plot out successive terms of the sequence, right, we start with 1 for n equals 1 to infinity. All right, we start out with 1/2, and we get larger for every term, so we could compare n plus 1 to a sub n to see that we're increasing. And so we can see that graphically here. We're monotonically increasing, but are we bounded? Visually, it looks like it, but we want to verify that algebraically. And so if we go and take the limit here as n goes to infinity, we want to divide by the largest shared power of n. So we get 1 plus 1 over n to the 3 halves. And of course, this goes to 0. So this whole thing goes to 1. And so we're increasing and we're bounded. Okay. For the next one, we're going to look at a slightly different one. So we're going to look at b sub n equals. Now we're going to throw a minus 1 to the n in there. All right, so for this one, you probably want to plot out some terms in here to see what's going on, because this is a little more complicated. Okay, for even powers of n, b sub n produces a positive terms, and so the even terms approach 1. It's just like for even values of n, b sub n is just like a sub n. And so for even values, they seem to approach 1. But for negative or odd values of n, b sub n terms are negative, and so they're getting smaller. And so they seem to be approaching minus 1. Well, remember, the rule on a limit is it has to be unique, right? And this isn't unique. As we get larger and larger values of n, we're going to be bouncing back and forth between minus 1 and 1 each term. Okay, so the conclusion in this case for the sequence b sub n is that the limit does not exist. Okay. All right. Next example here. Okay, the next example, we'll look at a sub n equals 0.75 to the n. Now, this is an example of a particular type of sequence that you may have seen once upon a time called a geometric sequence. And we have some rules about geometric sequences. Okay, geometric sequences have a general form r to the n. Okay, so a sub n equals some ratio r to the n power. Well, if r is less than 1, then the geometric sequences converge. Okay, it converges. In this case, we have a geometric sequence. 0.75 is r. That is less than 1. Okay, that's between 0 and 1. So the sequence converges to 0, and it is monotonic. Okay, let me real quick give you the general form of a geometric sequence. A geometric sequence that down so you can see, has the form AR to the N, where A is a constant and R is our ratio, right? So if R is between 0 and 1, then the geometric sequence converges. Okay. So that's something you may have seen once upon a time before. Okay, so in our case here, our geometric sequence has the constant equals 1, R is 0.75, and since that is less than 1 but greater than 0, the sequence converges to 0 and is monotonic. Okay, now, next one, negative R to the N. Well, I can write that as negative 1 to the N, R to the N, and so that is we can see from that that's going to, since the geometric sequence part of that, so we're looking at two sequences, okay? The -1 to the n part, the r to the n. The r to the n part, because it's negative 0.75, we can write that as -1 to the n times 0.75 to the n, and that sequence of 0.75 to the n is going to converge to 0. The -1 to the n is going to make it that's going to oscillate back and forth between -1 and 1, but the product of those two is going to, while still oscillating positive and negative, it will converge to 0. Okay, so it oscillates and converges to 0. Okay, so it goes without saying, though, this particular one, well, it doesn't go without saying, that's why I'm saying it. This particular sequence is an example of one that is not, it does converge, but it's not monotonic. Okay, it is not monotonic. Okay, it is, however, bounded. Okay, so even though it's not monotonic, it is, however, bounded. It's bounded for, we're talking n equals 0 to infinity, say, and we can see it's bounded between for 0.75, right? So it's bounded between 0.75 and negative 0.75. So it lives within that range. And it converges to 0, but we have bounded above and below. The terms are all contained within there. So it is a bounded sequence because it is bounded and it converges. Okay, finally, another example of a geometric sequence, but this one 1.15 to the n. Since the ratio is greater than 1, r is greater than 1, the sequence diverges. Okay, it's monotonic, it's increasing, okay, but it diverges in this case. It does not have an upper bound. All right, and again, another variation on the geometric. We'll take that 1.15 and we'll throw a -1 in front of it. So that becomes -1 to the n times r to the n. Well, the r is what drives this here. And because that's greater than 1, it diverges. Okay. And it also oscillates. It's not monotonic. It flips as -1 to the n. As n goes odd to even, it flips back and forth between positive and negative. So we can roll all this together into a theorem on geometric sequences. Okay. If r is a real number, the limit as n goes to infinity of r to the n, if the absolute value of r is less than 1, okay, so it's contained between 1 and -1, then the sequence converges to 0. If r equals 1, it converges to 1. And if r is less than or equal to -1 or greater than 1, then it diverges. The limit does not exist. It diverges. Okay. If r is less than 0, then the geometric sequence oscillates. Okay. Finally, if r is greater than 0, it's a monotonic sequence. So that, move to the next topic now. Now, when way back in Calc 1, when you first started talking about limits, you had uh, we had certain limits that were a little tricky to evaluate. So we used a theorem that we called the sandwich theorem or the squeeze theorem. Okay, where if I found uh, two functions that bounded my third function, a lower and an upper bound, and those two functions had the same limit, then the squeeze theorem said that middle one also had to have that limit. And we have the same theorem for sequences. So if I have a sub n, b sub n, and c sub n are sequences such that the a sub n terms are always less than or equal to b sub n terms, always less than or equal to c sub n for all integers n, greater than some index. Okay, so to use the squeeze theorem for sequences, it isn't that it has to be true for all values of n, just past some point. Okay, for some large enough value of n, this has to be true. And then the limit, if the limit as n goes to infinity of a sub n is the limit as n goes to infinity of c sub n, then the limit as n goes to infinity of b sub n must also be that same limit L. Okay, so we can look at an example here, okay, to use the squeeze theorem, but this is basically what we're saying here. We're saying, all right, b sub n is what I care about, okay, but it's hard to look at that directly. But I have another sequence a sub n that's always less than or equal to b sub n, and I have a sequence c sub n that's always greater than or equal to b sub n, and a sub n and c sub n both go to the same limit L. Well, then b sub n has to go there too. Okay, so we can look at an example here. Okay, suppose my sequence is cosine n over n squared plus 1. Okay, I want to know what happens to that, but if I look at a sub n, and I know cosine is always between -1 and c sub n is going to be 1 over n squared plus 1. Okay, so if a sub n and c sub n are that, then a sub n is always less than or equal to b sub n, always less than or equal to c sub n, right? Okay, -1 less than or equal to -1 over n squared plus 1 is less than or equal to cosine of n. Okay, I can't look at that directly, right? Because cosine of n always bounces, it's going to oscillate around. It's going to range between -1 and 1, so it can't just plug in and see what happens. So I need something like this to help me out. Again, I'll do the same thing. Look at the limit as n goes to infinity. And I want the limit as n goes to infinity of the middle one, right? Okay, divide everything by n squared. Okay, so 0, 0. So this goes to 0. And same thing with this one. We divide it by n squared. So this one also goes to 0. Okay, both the top and bottom limit go to 0. And so we conclude that by the squeeze theorem, right, the limit as n goes to infinity of cosine n over n squared plus 1 also has to be 0 by the Squeaks theorem. Okay, so that is our squeeze theorem. Okay, just a graphical depiction of what we just looked at. All right, so the next thing then is a theorem that we have for bounded monotonic sequences. Okay. Um, a and that says this. Okay. A bounded monotonic sequence convergence. Okay, so you could look at that, think about it this way. You pour a cup of hot coffee, put it on your desk to cool. Every minute, we're going to measure the temperature of the coffee, and we're going to create a sequence of temperature readings. The sequence has two key properties. The first is the terms of the sequence are decreasing because the temperature is cooling, right? And secondly, the sequence is bounded below because the coffee is not going to get any colder than the surrounding temperature. Okay. In fact, the measurements, if they continue indefinitely, the sequence of temperatures converges to the temperature in the room. That is a classic example, a nice example from everyday physics that illustrates the importance of this importance of this theorem that characterizes convergent sequences in terms of boundedness and monotonicity. And remember, monotonicity is non-decreasing or non-increasing, either one. Okay, a bounded monotonic sequence converges, and so we could be talking about a non-decreasing sequence that is bounded above. We could be talking about a non-increasing sequence bounded below, as in our cooling example. Either way, okay, and to give you a nice also everyday thing, suppose I have a cup of ice water and I'm going to set it in a room, and I'm going to do the same thing, take temperature readings, right? Every successive temperature reading is going to be warmer than the last. Okay, the temperature is going to be increasing, and it's going to be bounded above by the room temperature. It's not going to get any hotter than the surrounding temperature. Okay, so whether we're talking about monotonic increasing, we call it, so that's monotonic, but it's non-decreasing, bounded above. We're talking about non-increasing, bounded below. The theorem is the same. We know that it converges. Okay. All right, so now we're going to finish up with an example here um, that also illustrates using recurrence relations. Okay, so we've looked at this chart. We talked about it before, where um, we could express the sequence either as a function f of n, or we could express it in terms of the n plus first term in terms of the nth term. And so we're going to look at an example with recurrence relations here. Um, and so that is the following here. So suppose that your doctor prescribes a dose of antibiotics for you. Okay. 100 milligram dose of an antibiotic taken every 12 hours. And the drug is known to have a half-life of 12 hours. So that is every 12 hours, half the drug in your blood is eliminated. And we want to do three things. We want to find the sequence that gives the amount of drug in your blood immediately after each dose, and then look at the graph of this to propose the limit of the sequence okay, which in the long run, how much drug do you need to have in your blood, and then find the limit of the sequence directly, okay? So those are the three things we're going to do. We'll start with the first one, finding a recurrence relation for this. So the first is our sequence, and so we see that we have, all right, d sub n will be the amount after the nth dose, for n equals 1, 2, 3, and so on, and d1 is 100 milligrams. And what we've said is after the n plus first dose, okay, we're going to have 100 milligrams, because that's the dose we have, plus, because of the half-life, you're doing this every 12 hours, and every 12 hours, half of the drug dissipates, half of the medication dissipates. So d sub n plus 1 will be 100 plus 0.5 n. All right, so now let's look at okay, so if we graph these terms, okay, we start with 100, then 150, 175, and so on, and we can see it looks like from the successive terms, it looks like we have a steady state level of 200, okay? So it appears that after 10 doses, it's 5 days, the amount of antibiotic in your blood is close to 200 milligrams, and importantly, it never exceeds that, okay? So in other words, it's not building up higher and higher at ever increasing levels, or the antibiotic would kill you, right? You're absorbing it at a certain rate, and so it seems to have a steady state. Now we want to look at, so it looks, we have evidence the terms of the sequence are increasing. Looks like they're bounded above by 200, okay? But we need to prove both of these facts, okay? And so we're going to do that here. Okay, so the first thing is we note that D1 equals our first dose, right, is 100, okay, which is less than 200. And what we'll do, so now we're going to use a tool called induction. So what we're going to do is we're going to suppose okay, so we assume that if dk is less than 200 for k greater than 1, induction says now we want to show that k plus 1 is. Okay, so the recurrence relation says that dk plus 1 is going to be 0.5 times dk plus 100. Well, since dk is less, since we are assuming, so proof by induction, right? That's a tool we used, you may have used before. Okay, and what that means is you assume you have to show that it's true for D1. Okay, and we know that D1 is 100, so that's less than 200. And what we'll do then is we'll assume it's true for DK and show that that means it has to be true for DK plus 1. That's how proof by induction works. So we know it's true for D1. We'll assume it's true for DK. Okay, and so dk plus 1, that's 0.5 dk plus 100. Okay, well, since dk is less than 200, 0.5 dk is less than 100. And so we get dk plus 1 is less than 200. And so, boom, we've proved proof by induction. So what we've done is we've shown that, right, by induction, our sequence is bounded. Okay. All right. So it's bounded. Now we need to prove dk is increasing, right? So we can look at that. We'll look at that this way. So this is, we've shown bounded here. Okay, now we're going to look at dk plus 1 minus dk. Okay, 0.5 dk plus 1 plus 100 minus 0.5 dk plus 100. So the 100s cancel. I get 0.5. Oh, hold on. I made a little bit of a boo-boo here. All right. Okay, so dk plus 1 minus dk. dk plus 1 is 100 plus 0.5 dk. We're going to subtract 0.5 dk. So that's just going to be 100. Okay, that's greater than 0. Okay, and so we get increasing monotonic. Okay. If we show that dk plus 1 minus dk is less than 0, that would mean we're decreasing. Okay, but we've shown that it's greater than 0, so it's increasing monotonic. And so we have bounded, monotonic, increasing. That means converges. Okay. All right. All right. So next is growth rates of sequences. And this is the same thing that we talked about in Calc 1. We talked about relative growth rates of functions. We're going to apply that same thinking to growth rates of sequences. Okay. So following sequences ordered according to increasing growth rates. Okay. So if A sub n appears before B sub n, then the limit as n goes to infinity of A sub n over B sub n is 0. We're saying B sub n grows faster than A sub n. Okay. That's what we're saying. The limit as n goes to infinity of B sub n over A sub n is infinity. B sub n grows faster. Okay. So natural log power q to the n. Okay. Grows less fast than n to the p. And this is for positive real numbers, p, q, r, s, where b is greater than 1. Okay. N to the p does not grow as fast as n to the p times the natural log of n to the r power. N to the p plus s grows faster than that. B to the n grows faster than n to the p plus s if b is greater than 1. N factorial, okay, and faster than all of those is n to the n. Okay, so that just kind of gives you a a range, some benchmark sequences. So the factorial is way up there. Factorial grows really fast. You're going to see factorials a lot in upcoming applications. Okay, and we talk about certain types of series. Okay. So just for relative comparison, right, we look at 10 to the n and n factorial. And if you look at the first 25 terms, say, it looks like 10 to the n's because 10 to the n is always larger than n factorial. But n factorial very quickly blows past things. Okay. Past n equals 25, n factorial is bigger than 10 to the n and very quickly gets much, much larger. Now, this is a log scale. This is a log base 10 scale because the numbers would be so huge here. So, but very quickly it blasts by. All right, final topic is the limit of a sequence. Okay, so the formal definition of the limit of a sequence, and we can do some examples with that. If I'll try and do some examples of that in an upcoming thing. But the formal definition of the limit of a sequence is very, very similar to the formal definition of the limit of a function. Okay, a sequence a sub n converges to a limit L, provided the terms of a sub n can be made arbitrarily close to L by taking n sufficiently large. Okay, so if for any epsilon greater than 0, I can find a positive integer n such that the absolute value of a sub n minus L is less than epsilon, then L is the limit of the sequence. Okay, so this is just like the formal definition for a function. You pick an epsilon greater than 0. Doesn't matter how small it is. Doesn't matter how tiny. Doesn't 0.00, however many zeros you want. 1. Okay? Doesn't matter how small epsilon is. You pick any tiny number epsilon, and I can find a large enough value of n. I can find a term in the sequence far enough along such that past that, the absolute value of a sub n minus L is less than that tiny number. Okay? And we say that the limit of the sequence is L. The sequence converges to L. And we can write that like we would. Limit as n goes to infinity of a sub n equals L. A sequence that does not converge is said to diverge. So let's see. I think that's it. Okay, that's the last topic for sequences. But here's kind of this is just a graphical, right, depiction of it to illustrate the concept. Okay, where we're saying, all right, what we're saying is that if the sequence a sub n converges to L, then for any epsilon greater than 0, I can find so where here's L, imagine a line drawn across here's L. If the sequence converges to L, then for any epsilon greater than 0, I can find a value n such that for terms past that big N term, the a sub n's are going to be between L plus epsilon and L plus minus epsilon. Okay, they're going to be within epsilon of that value, no matter what epsilon is. So the smaller epsilon is, the tighter the range is going to be. But it doesn't matter because I find large enough term in the sequence, and past that, they're going to be within that range. Okay, that's the formal. And you may recognize this as being very similar to what we had with with the functions the same, analogous idea. All right, that's it. Next up will be infinite series.